All right, so here we have an electrical energy problem, a proton moving parallel to a uniform electric field. We're given the strength of the electric field is 450 Newton per Coulomb, which is equivalent to 450 volts per meter. Newton per Coulomb is the force perspective. What that's saying is if you stuck a charge in this field, and if that charge were 1 Coulomb, then the force that the field would exert would be equal to 450 newtons. The other way to look at electric field is in terms of volt per meter. And you can show, just by doing unit analysis, that a Newton per Coulomb is equivalent to a volt per meter. That'd be a good exercise to do, which I won't show right now, just for sake of time. But what does volt per meter mean? What it means is that the potential difference between 2 points that are 1 meter apart it would be 450 volts. So, let's say, A and B. Let's just say hypothetically that point A and point B are 1 meter apart. So the electric field being 450 volts per meter, that means that the potential difference would be 450 volts. So if point A and B were 2 meters apart, then the potential difference would be 900 volts. So volt per meter and Newton per Coulomb. Newton per Coulomb is a force perspective, and volt per meter is the energy perspective. All right, so let's take a look at the questions. The first question is, if the proton moves 3.5 centimeters, which is 0.035 meters, what is the work done by the electric field? So what I want to do is come over here. I have the Earth with the gravitational field shown. So, what happens in an electric field is remarkably similar to what happens in a gravitational field. So if we put a mass in the Earth's gravitational field, as the mass falls, work is being done by gravity. The basic work equation, I have it up here. The basic work equation is work equals Fd, force times distance. So the force of a gravitational field, is mg, where m is the mass of that mass in the field, and then d is the height that the mass falls through, how far the mass goes. And remember, whenever you use the work equation, force and distance must be parallel. So we're just going to change this d to an h, so F times h, where h is the distance. And if we're looking for the work done by the gravitational field, then that's the force of the gravitational field. And we know that the force of the gravitational field is equal to mg. So this becomes mgh, which should look familiar. That's the equation for potential energy of gravity. So this is something we talked about first semester. The work done by a gravitational field is always equal to the change in the potential energy of the object. And, work is positive if it's being done in the direction of motion, which is what's happening in this case here. This mass is falling, it's going with the gravitational field, so that would be considered positive work. If the mass were thrown up the gravitational field, then we would say that the gravitational field does negative work because it's opposite the motion. All right, so let's come over here and look at the proton moving through this electric field. So there is a force. The force on the proton is the force of the electric field, which is equal to QE, where this Q is absolute valued. So the force of an electric field is QE, and then the distance being moved is this D here. So for question A, the work of the electric field is going to be equal to the force of the electric field times the distance. So notice it's very similar to what we did with gravity. Okay, the force of the electric field, it's equal to QE. So this is equal to Q E, and then there's the D. So force of the electric field is the QE, and D is the distance. So notice that this QED here is basically the same thing as MGH. The Q becomes M. You know, gravitational fields exert force on mass. Electric fields exert force on charge. So the Q becomes M. The E becomes G. And then D is the distance, and over here, H is the distance. And again, in the work equation, the force and the distance must be parallel, which they are here. So now we plug the numbers in. So the work done by the electric field is equal to, let's see, the charge of a proton is 1.6 times 10 to the negative 19 coulombs. The electric field is 450 Newton per coulomb, and the distance moved is 0.035 meters. So this gives us work of the electric field equal to 2.52 times 10 to the negative 18 joules. And that's positive, and the reason it's positive is the work is being done in the direction of motion. That's the definition of positive work. And just to take a look here, how did we get joules? Well, the coulombs up here canceled. The coulombs canceled, and we're left with Newton times meter, which is a joule. A Newton times a meter is a joule. All right, so that's A. B, what potential difference or voltage does the proton move through? So here's where we're going to use the fourth equation on my list of equations. But before we do it, I just want to talk about, the fact that this answer is going to come out negative. One thing you should be aware of is as you move down an electric field, volts always get smaller. And the reason for this is that the definition of volt, or electric potential, is potential energy per charge, and everything in physics is based on a little positive guy. So as a little positive guy travels down the electric field, his potential energy is getting smaller. And if the potential energy is getting smaller, the volts are getting smaller. So the answer to question B is negative because the proton ends on a smaller electric potential, or volts, and starts at a higher. So you're going to be going smaller volts minus bigger volts. So the equation is delta V, the potential difference, is equal to negative ED. And I should also mention, the only time you can use this equation is when the electric field is uniform or constant, which means you're between oppositely charged parallel plates. All right, so the potential difference is going to be negative. The electric field is 450 Newton per coulomb, and the distance between the 2 points is 0.035 meters. And so this comes out as negative 15.75. Now, as we said a second ago, a Newton times a meter is a joule. So we have joule per coulomb, and a joule per coulomb is a volt, negative 15.75 volts. Okay, and then also, I'll just mention, we could have looked at, this actually would have been a nice time to use the electric field as volt per meter, because here I did Newton per coulomb, but let's just resolve it one more time. Negative 450 volt per meter, and then the distance is 0.035. So now the meters cancel, and you come out with volt without having to, go through the joule per coulomb step there. All right, and then question C, let's shrink this all down. Make room for part C. There we go, shrink this down. Put it there. All right, now part C, what we're asked to solve for is the the change in the potential energy of the proton. So here's where we use equation 3. So part C, we're going to say potential difference, which we now know is change in potential energy per charge. So the change of potential energy, which by the way is equal to the work. You know, we saw that with the gravitational field. You know, mgh in a gravitational field becomes QED. So we actually know the answer to this already. It's the answer to part A, but just here's another way to look at it. So we have that, and let's see, the potential difference from A to B was negative 15.75. Now a volt is a joule per coulomb, and then the charge of a proton is 1.6 times 10 to the negative 19 coulombs. The coulombs cancel, and we get a change in potential energy equal to negative 2.52 times 10 to the negative 18 joules. Which means, now the problem doesn't ask for this, but we just, I'll mention it real quickly. The change in kinetic energy, assuming no friction, would be positive 2.52 times 10 to the negative 18. That's just conservation of energy. As the proton travels through the electric field, it's losing potential energy and simultaneously gaining kinetic, just like a mass falling through a gravitational field. And then another question that could have been asked is, well, what's the velocity of the proton after traveling through this distance? So the way you would find the velocity of the proton is, now we have the change in kinetic, so then you go, okay, well, the kinetic energy of the proton when it's done traveling this distance, kinetic energy is 1/2 mv squared, where v is now velocity, and you could solve this for the velocity of the proton.